In the previous videos, we learned how to name alkanes and cycloalkanes, and the last thing we have to talk about is their physical properties. You will find that alkanes aren't all that interesting in terms of reactivity. They don't do a whole lot, which is why they're usually used as solvents. So they dissolve other compounds and enable other compounds to react, but they don't really react themselves. So really the only reaction that alkanes do is combustion. They're quite flammable, but that's about the only reaction that they do. So if you recall way back in the day when we talked about inorganic chemistry, we said that hydrocarbons do combustion reactions, and we drew up this generic formula of CXHY saying that this could be any number of carbons and the number of hydrogens can vary accordingly. So this is some type of hydrocarbon. We're not really being specific what type. And if that reacts with oxygen, it's going to produce carbon dioxide and water. And since alkanes are hydrocarbons, they fall into this category and they do combustion reactions. Because they do combustion reactions, they are commonly used as fuels. So for example, if you've ever used a propane tank or butane in a lighter, you have used alkanes as fuels. Before we get into the properties, I think it's useful to think about their intermolecular forces. So right here, I drew pentane, and if we were to expand this out, we would see that it has 5 carbons, and the carbon at the very front has 1 bond, so it needs 3 hydrogens to complete its octet. Same thing with this carbon at the end. And then the carbons in the middle, each one has 2 bonds, so it needs 2 hydrogens to complete its octet. And that's the case for all of them. Notice that in this molecule, we only have carbon-carbon bonds and carbon-hydrogen bonds, the entire molecule. And if you think back to when we talked about polar and nonpolar bonds, we said that in order to determine whether a bond is polar or nonpolar, we will calculate its electronegativity difference. Well, if carbon is bonded to itself, there is no electronegativity difference. It's the same. So the carbon-carbon bond is nonpolar. The carbon-hydrogen bond is also nonpolar. Its electronegativity difference is very small, and you could go back and calculate that if you don't remember that. So this is also a nonpolar bond. Well, we said to determine whether a molecule is polar or nonpolar, in order to be a polar molecule, it has to have at least 1 polar bond. And if it doesn't have any polar bonds, it's automatically nonpolar. And notice that this alkane doesn't have any polar bonds. So this is a nonpolar molecule. And the only intermolecular force it has as a nonpolar molecule is dispersion. So only dispersion interactions are present in alkanes. Remember that dispersion intermolecular forces are the weakest. So individual intermolecular forces that are dispersion, not particularly strong. So if I had a whole bunch of pentane molecules, they would be attracted to each other via dispersion. And these little lines that I'm doodling over here, these are representing our dispersion interactions. And these are intermolecular forces because they are holding the individual molecules attracted to each other. So the stronger that the intermolecular force is, the more energy it takes to pull these molecules apart from each other. And if it takes more energy to do that, that means that its melting point and boiling point will be high because you have to put a lot of energy into the system to break those intermolecular forces and get the molecules apart from each other. Well, we said alkanes only have dispersion, which is the weakest intermolecular force, so it doesn't take all that much energy to get these things to melt or to boil. which is why if alkanes are very small, so if they are anywhere between 1 to 4 carbons, they tend to be gases at room temperature. So for example, this is where propane and butane come in, and this is why they are very, very volatile. Very easy for them to become a gas. Propane is definitely a gas at room temperature. Once we get to the 5 to 8 carbon range, these tend to be liquids at room temperature. And I would like to think about this. So if we're looking at propane, it only has 3 carbons. And we know that each of these dispersion interactions are very weak. So each individual dispersion interaction, the weakest intermolecular force. However, if we look at, let's say, octane, it also has dispersion. And even though each intermolecular force here is weak, the fact that we have more of them collectively becomes a stronger interaction than propane, which only has 3 carbons and has a limited number of dispersion interactions. So this has more dispersion forces, which means it has a higher melting point. Ooh, that's a G. Higher melting point and a higher boiling point. And that's going to be a trend across the board. So you'll see the more carbons you have, the higher the melting point and the higher the boiling point. So between 5 and 8 carbons, these tend to be liquids because they have higher melting points and higher boiling points. And gasoline is an example of that. So octane is used in gasoline. Once we get between 6 to 17 carbons, they still tend to be liquids, but they are more viscous liquids. So they will have like a thicker texture. And examples here would be kerosene or jet fuel. And finally, when we get beyond 18 carbons, so 18 carbons or more, these start to become solids, but they are waxy solids. So they still have kind of a soft texture. And examples of that would be beeswax or petroleum jelly, which is Vaseline. All right, so in summary, more carbons means higher melting point and higher boiling point due to the fact that they have more dispersion interactions. Even though each dispersion interaction is weak, if you stack a whole bunch of them, they become collectively stronger.